So here we have a board out of an Electrolux stove, and as you can see here, there's a couple of resistors burned up, one on each side. The one on the one side there has really created a smoke show on the surrounding connectors. This one's not too bad. So we'll get some of the soot cleaned off the top of the board first so we can see what the damage is. On the bottom of the board there's this trace here that's burned up, and a couple of the pads look a little toasty. So we'll see what we can do with that. See, that pad there got kind of warm and the solder is oxidized. It's got pretty hot. So first of all, we'll get these relays out of the road so that we can get access to the area. A guy could work around all this, but it's just faster to get everything out of the road. It doesn't take any time at all. Now you get all kinds of room. This relay here was right next to the resistor that burned up. I don't know if you can see, it's still got a bunch of soot all over it, but the one side got quite a chunk burned out of it. So I'm not sure if the relay itself is damaged. I'll get some of the soot off and then we'll take a look. The other one had some smoke on it too, but it doesn't have as much damage. It's a really rough surface. There's all kinds of cotton caught in there from the Q-tip. Of course, rubbing more cotton on it doesn't help. But you can see there's quite a divot taken out of the side of there. Just trying to see if it's actually made its way into the inside of the relay, perforated the casing or not. These relays are not airtight anyway. There is a vent on the top, so it's not the end of the world if there's some air gets in there, but you don't want it warping the insides of the relay. This one here's got a heat mark on the outside, but it's not, there's no hole burned in it like the other one. I think we'll be okay here. So we should make sure, especially with that little relay that's got the side scorched on it, whether these relays are still working. So the clips are hooked to the meter, and the probes that you see to the right there are actually from a power supply for 12 volts. These are both 12 volt coil relays. So I'll just hook a multimeter across and we'll see if the relay actually conducts when we trigger the relay. Trigger the coil, I mean. And as you can see, it still connects just fine, so the relay is good. Whether we decide to use it or not is something we'll decide later. So first we'll check the normally closed contacts on this relay, because it's a Form C or a single pull double throw. And then we'll connect the relay, connect the meter to the normally open contacts and confirm that they close when the coil is energized. One of my clips doesn't want to close there. So apply 12 volts to the coil, and yes, the contacts are fine. So now we'll take a closer look at the damage to the board. If I'm going to replace these resistors, I need to figure out what value they are. I assume they are the same value, both resistors. As you can see, there's not much left of that one. There's no way to read the color bands off it or anything. Yeah, I look at it from the left and the right, and there's just nothing left. Just a smear. The other one, though, didn't get hit as hard. So hopefully we can figure out what the color code is on here. Shooting from the top didn't gain us anything, but here you can see I took a picture from the side, and you can see the color codes. So we should be able to come up with something close. We'll have to analyze what this resistor does in the circuit and see how precise we need to be with that value. You got to be careful when using a desoldering gun on loose leads like that, because you can suck the loose leads directly into the soldering gun. Trying to be careful here because the pads on the bottom got hot enough that I doubt they're still glued down, so I don't want to tear them. So I'm just trying to be gentle. Just use the tip of the tweezers to poke that through there. Fingernails easier to control, so use that for this one. And try not to break this resistor up so that we can look at it when we get it out. I think I know the color codes on it, but I'm just the way this resistor is damaged, it looks like the top is damaged but the bottom isn't, so we'll get if we can keep the resistor in one piece, we can look at the underside of it. Should be pretty clear. And there's the color codes we got off of there. This is kind of an unusual resistor based on what it does in the circuit, which does not appear to be a precision application. They went with a 0.05% tolerance resistor, which is crazy high tolerance for what they're doing. I would think 5% would probably be sufficient. So the burned residue from the resistor is conductive, so you want to clean that off the board. I'm just checking here to make sure the remains, like the board is burned a little bit there too, so just making sure that's not conductive. As you can see, it's not I couldn't get a reading off it. They're just checking my probes to make sure everything's connected. I forget what the limit of this meter is, 20 mega ohms or something like that, and it wasn't even giving a reading of any sort, so for the purposes of this board, that's fine. So there's what we're left with. You could Dremel all the burnt stuff off, but then you'd probably end up with a hole in your board. And there are traces underneath, so I'm just gonna leave it this way. It looks a little ugly, but it's functional. Just checking the traces underneath, and like I suspected, they got hot enough that the adhesive underneath kind of let go a little bit. However, the copper trace itself appears to be intact. It's not torn or burned through or anything like that, so as long as we're careful when we reassemble it, we should be able to just reuse these pads as is. So this is how I found something interesting. I didn't get it on camera, but when I measured those two pins there was no conductivity. And I'll show you why in a minute here. That's why. That solder joint had broken. So from here, you can see as I'm moving this around that whole pin moves. And this is the main, well, I'll show you a circuit in a minute here. But this is the main power feed for part of the circuit. And you can see that all these pins are, most of these pins, the solder joints are broken on them. So just an explanatory note here. This board, the power to run the relay coils comes from this transformer, so it's 12 volt or whatever. Rough figuring, each relay coil will pull about a watt, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 relays times a watt plus some for running the logic and all that. Figure 20 watts. Maybe a bit more. So this relay, or transformer rather, is powered from J4. That's this jack here. So pin 1 is neutral, pin 3 is 120 volts. Now, as you just saw in the microscope, the jacks, these jacks, the pins break in them, the solder joints break. So if neutral breaks, pin 1, transformer 1 is cut off from power. It still has 120 volts, but if it can't get neutral, where is it going to get neutral from? Well, it's going to pull neutral from the other jack through these normally closed pins on the relay and these two resistors from jack 3 here. Now, so you're pulling 20 watts of power through a couple of quarter watt resistors. We can't handle that, that's why everything burns up. So based on the circuit that we just saw there, they're using these two resistors basically to pull both sides of the oven element to neutral when the element is off. I don't understand why they would do this. Maybe as a safety thing if you were in danger of touching something. These resistors here are just what I had on hand. Given the purpose of the resistors, which is just to pull the element to neutral, 238 ohms, 239 is fine. The originals were 231. This will be fine. But if those resistors, if any power fault happened to that element, 120 volts from either side, were to touch that element, it would take absolutely nothing at all to overwhelm a quarter-watt resistor. So there's no real safety there. Or maybe what they were thinking is they want this resistor to light on fire if there's any electrical fault. That doesn't make any sense either. There are better ways to alert the consumer to an electrical fault than lighting the whole thing on fire on purpose. So I don't know what the engineer was thinking here, but the circuit should function just fine without those resistors in place. I mean, the board will still go screwy when those solder joints break, but at least it won't light on fire. However, we'll replace them because maybe there's some purpose there I missed. As far as I can tell with circuitry, another possible reason they could have resistors there is for voltage monitoring, but I don't see any inputs off of the circuit board for voltage monitoring. It's a very bare, very simple circuit for this part of the circuit. All the wiring goes direct to the oven elements. There's no feedback to the controller, which is on a different board. As far as I can tell, anyway. So when we put these resistors in place, we'll make sure that they're pulled tight to the board so that there's no downward pressure on those damaged circuit traces that would be able to push the traces away from the board. Right now, if you didn't pull the resistor down tight to the board, if there was a gap there and you pushed on the top of the resistor, it would just push that trace away from the board. Rip it. Let's clean up our solder flux residue here. It's kind of silly being so tidy on a board like this that's got great big scorch marks on it, but anyway, it's a good habit to get into and just cleaning up after yourself. So now I'll stick those two relays back on the board. I did think better of this later on, and I came back and put a brand new relay in this spot instead of the one with the hole burned in it, and I just kept the old one for a spare. Sometime if I have to fix something and I don't have a brand new one of the correct size, I'll just use that one. It does work fine, as we saw, but it just kind of looks ugly, so I changed it again. One thing you have to be careful with when you're soldering big items like this is to make sure that they stay tucked down to the board, which is why I've wedged some sticky notes underneath. Pads of sticky notes. There's like a 3/4 of an inch of material there. I think there's 2 pads of sticky notes. Just to keep some pressure on it, keep it tight to the board while I'm soldering. Because again, if you have something sticking up from the board and it gets pushed down on, there's nothing holding it there but the adhesive of the copper circuit trace. These boards are single layer boards, which is part of the reason why the connectors, solder joints on the connectors break. With a double-sided board, typically all the holes are plated through, so you have a lot more material there for the solder to bond to. With a single layer board, you just have a thin membrane of copper holding everything, and the solder joint is relatively thin to what it would be for a double-sided board. The double-sided board would wicks the solder right through the board, so there's a lot more strength there. It's not the traces that are lifting off this board, though. It is actually the solder joints breaking, as you saw in the microscope shots. The solder I'm using is leaded solder, which should be a little more forgiving than the lead-free that they have to use in the factory. That might also be a factor in why the solder joints are breaking. They don't look like they were bad solder joints, and it's not the point. It's not where the solder meets the pin that is breaking. It's actually the solder in the middle of the joint that's breaking. So I don't think it was really a soldering error at the factory. It's just a weak design. But anyway, lead solder is a little more malleable. It's got a little more flex to it than lead-free solder does. So hopefully they won't have this problem again with this board. So I did the math, measured the width on that blown trace there, and it works out to about the equivalent of 30 gauge copper. So I scrounged up a roll of old LAN cable here. And this stuff is 24 gauge, so as long as you put more copper in there than you had originally, you'll be fine. Yeah, don't play with razors. It's a good way to bleed. Just very lightly scoring the jacket here so that I can pull it apart. You don't want to nick the wires. These are solid wires, so they're more difficult to work with than stranded wires. Some days I like to suffer, I guess. So this is just how you skin LAN wire, if you didn't know. That thread in there, just wrap it around a screwdriver and pull. Slits the whole thing without risking nicking any wires. There was a bit on the end here that was chewed up, so I'll just chop that off. So I'm just getting it roughed into shape here. And then we'll spend a bit of time getting it all massaged into shape. Takes a little time. Some guys like using tweezers, or you can use dental picks. This wire was thick enough it was kind of hard to work with. Just try and follow that original trace as best you can. The screw hole there, I did end up having to put a little bit of a jog around that. This is just crazy glue. It bonds pretty well to PVC wire insulation and circuit boards. If you ever need to take this off of there, just use a Q-tip and some acetone and it'll dissolve. It wicks underneath, which is nice. And then if you want to be tidy, you can take a Q-tip and acetone alongside. I didn't get super fussy with this. You can see how I jogged around that screw hole there, because I don't know if there's going to be a plastic post right there, in which case it needs a little bit of room. So now we'll get the these are the main power jacks for these are the problem here, the ones that broke. So we're just gonna redo all the solder joints. Brittle solder in there that was in there obviously wasn't working, so I just sucked it all out of there and we'll just put lead solder. I could just reflow it, but then you're leaving the same solder in there that was the problem in the first place. I'll try and make this a little bit better. I'm not doing all the pins at once, because then it's hard to keep the connector straight up and down and lined up. So if you just do a few at a time, the rest of the pins will keep everything in place. I should also be doing the one on the end first. But anyway, I checked everything and everything was still straight and flat afterwards, tight to the board. Now we'll do the one on the other side. This one here, I think it's I forget if it's an 8 or 9 pin connector, but you notice I leave the solder in the 2 pins on the end, like I was saying, just to keep everything in place. So I'll do the 6 or 7 pins in the middle, and then I'll come back and I'll do the ones on the end. You see the one on either end is still soldered. And I think my camera gets high on flux fumes here. You don't want to apply too much heat here, you start melting the nylon collar that's around the pins. And now we'll do the 2 pins on the end. And the engineers at the Electrolux factory, they always leave these tabs on the zip ties, so we'll just do that properly so the next guy doesn't bleed so much. So that should be repaired. Now we need to test, make sure everything's okay. So our primary, or our transformer, should be about 96 ohms, just making sure we understand what pins go where. This is just some plug I scavenged off of some board somewhere along the line. Just wrapping up the wires we don't need. Make sure you observe which is neutral and which is hot. Pin 1 is neutral, pin 3 is hot in this connector. That light bulb you see there is just a limiter. It's a 40 watt appliance bulb in series with power feed. So if we accidentally short something out, that bulb will light brightly. And we'll also limit the power to 40 watts. So we shouldn't have any welding happening today or huge sparks or anything. It's just there as a safety, both for the board and for me. Just making sure, doing an idiot check here, making sure we understand what we're feeding power to before we feed power to it. And that those pins do go to the primary of the transformer. And we'll check the prongs of the power plug here should get 96 ohms if we have everything hooked up right. Yep, there you go. So I'm just connecting a connector here so that I have access to the ground for the signal input. We're using the main power transformer to provide 12 volt rails to the relay coils, but in order to trigger the relay coils, we're going to have to I want to use the logic on the board. So this is 5 volt input. I had to hotwire a couple things here because there's a couple safety lines. So now I'm going through all the relay inputs, all the 5 volt inputs. This is connected to a 5 volt power supply that you can't see on camera, and just making sure all the relays click by triggering the 5 volt lines. And this will prove that all the logic on the board is still okay. There's actually 2 safety lines, which are the couple of red jumper wires you see there. One of them requires a steady 5 volt signal, and the other one actually requires a pulsed 5 volt signal, which I thought was unusual. And if those 2 lines are not in that state, then you can apply 5 volt input to these pins and absolutely nothing happens. So I've seen worse designs in that regard. You can't accidentally trigger the relays. Can't accidentally leave an oven element on and burn the house down. Of course, what happens when the solder joints break, who knows, right? As we see when parts on the board start lighting on fire. So all 18 of the relays go click. I'm not really expecting any problems other than in that bake circuitry, which both the resistors are part of. So we know that the bake relays both trigger. And we've checked we've had one of them off the board and checked it for continuity. We need to check the other one yet. So here we'll just check both relays for continuity. The in and out pins there for the relay, as you can see, that's the only place they go. So I'm just directly connecting the meter to them using the clips, and then the probes I have in my hands here are 12 volt power supply. You can see that one clicks. We tested that one already, but just to be clear. Now we'll flip around to the other side. The 2 pins on the left there are wired together, as you can see. So it doesn't matter if you connect to one or both, just whatever. It was more convenient to hook to one. If you are connecting to manually trigger a relay like this, make sure you're using the correct polarity for the board. The relay won't care, but your support circuitry can be fried if you hook it up backwards. So it appears that everything works like it should, conducts and connects, so I'm going to call that fixed. Thanks for watching.